Hi, I know it's been a while. I'll be resuming videos on my channel now. I'm going to continue with number theory. Basically, I'm making a course on Udemy for an advanced number theory, and this is part of that course. A lot of the content for the course has already been created. I'm going to continue with number theory till I'm able to finish the course. So this video is about problem solving techniques in number theory, and I want to highlight one particular technique, which is factorization. So I'll show you how factorization is involved in lots of number theory problems and how you can use that in your Olympiad problem solving to get the solution really quickly. And I'll show that with a few examples. So I have around 10 problems that I wanted to show in this video. So let's just get started. So the first one is this. Let x, y, z be integers. And the condition that is given is that xy plus yz plus zx equals 1. Prove that the number 1 plus x square, 1 plus y square, 1 plus z square, the product, is a perfect square. Okay, so let's think about this particular problem. We have this condition, we have to use that somehow. So we have to also prove that this product is a perfect square. So in order to think about this, we can start by thinking of each of these terms, and 1 plus x square, you can always substitute xy plus yz plus zx for 1 here. So you will get xy plus yz plus zx plus x square, and notice that now you can factorize this. If you take y common here, you get x plus z, and if you take x common here, you get x plus z again. You get y, x plus z, plus x plus z, and basically this becomes y plus x times x plus z. Now that should give you an idea. The whole problem is going to be done in this way, because if we can factorize 1 plus x square as product of factors y plus x and x plus z, similarly you can do the same for 1 plus y square. I will do the same thing. I'll substitute for 1 xy plus yz plus zx plus y square, and then I'll take common between xy and y square. You'll get x plus y as a factor, and then you can take common between xz and yz by taking z common. And you will end up with basically y plus z times z plus x here. And similarly, we can also prove that 1 plus z square is equal to z plus x times y plus z. The same idea, we are using the condition given in the problem to actually factorize each of these terms. And each term is a product of two linear factors. Once you get this factorization, the product of all three of them is the product of 6 linear factors, out of which each factor is repeated twice. So it becomes a perfect square. You can say that this is going to be equal to x plus y plus z, z plus x whole square. So a simple problem, but the idea was key how to use this condition given in the question, right? So let's move on to the next one. Question number 2, find the greatest integer n, which is less than 1000, for which 4n cube minus 3n is the product of two consecutive odd integers. Okay, so we have to find the largest n, which is less than 1000, for which this quantity 4n cube minus 3n is the product of two consecutive odd numbers, right? So odd numbers always are in the form 2k plus 1. So you can take odd numbers like 2k plus 1, 2k plus 3. These are two consecutive odd integers. However, the better way to choose two consecutive odd integers would be 2k minus 1 and 2k plus 1. Because there you can use the identity a minus b into a plus b is a square minus b square, right? So what we'll do is we'll just say 4n cube minus 3n is equal to 2k minus 1 into 2k plus 1 as per the question, which becomes 4k square minus 1. And now we can sort of isolate this 4k square. We can say 4k square is equal to 4n cube minus 3n plus 1, right? Here, I can think about factorizing this because if it is a cubic, you should always think whether you can actually factorize the cubic or not. So if you look at it, n is equal to minus 1 is a root of this cubic polynomial. Think about it. 4 into minus 1, you get minus 1, minus 4, plus 3 plus 1. So that is clearly a root. That means n plus 1 is a factor. So you get 4n square n plus 1 and plus 4n square, so minus 4n n plus 1 minus 4n, so you get a plus n plus 1. So clearly we are able to factorize this and we are getting n plus 1 common and 4n square minus 4n plus 1. And notice that this is a perfect square. So this is becoming n plus 1 times 2n minus 1 whole square, right? And that is equal to 4k square. So think about it. We are getting an inequality. 4k square is equal to this quantity, but 2n minus 1 is an odd integer. So this is odd. And this is a square also, right? So what we get from here is this side 4 times k square is an even number. And this side here, this is odd. So this must be even. So n plus 1 must be even. Because both sides, the parity should be the same. If this side is even, this side has to be even. But 2n minus 1 whole square cannot be even. So therefore, n plus 1 must be even. And also notice that this is a perfect square. This is 2k whole square, a perfect square. And here there is a square term. So how can a perfect square be equal to something that is not a perfect square? So that is not possible. So if this side, left hand side is a perfect square, right hand side also has to be a perfect square, which means 2n minus 1 whole square is already a perfect square. So that doesn't bother us. But n plus 1 so far was not a perfect square. So now we know n plus 1 must be a perfect square, right? So we are using parity and the fact that the LHS is a perfect square to prove that n plus 1 also is a perfect square and it also must be even, right? So now we will just think about it. N plus 1 is a perfect square and is even. Perfect square and is even. Which means we have to look for the largest perfect square less than 1000. So which is also even, right? So 30 square is 900. After that 31 square becomes 961 and 32 square becomes 1024. So basically 32 square cannot be taken because it becomes bigger than 1000. 31 square is odd. So n plus 1 has to be an even perfect square. So n plus 1 must be 900, which is 30 square. And that gives us the value of n. N is 899. So that is the logic for this particular problem. I hope you are understanding what I'm doing here. It is not very difficult. It's just we are taking into account parity and we are also taking into account that one side was a perfect square. So the other side also must be perfect square. Okay, let's move on to the next problem. Find all pairs A comma B of positive integers such that a square minus 4b square is equal to a minus 2b plus 2 power 2 of 2022. This is an actual Olympiad problem. I'm forgetting the country. I think it's Poland. It's an Olympiad problem. Let's see how to approach this. All pairs A and B of positive integers such that this happens. This is true. Now, it is obvious here that you will use this identity a minus 2b into a plus 2b and bring a minus 2b this side is equal to 2 power 2022. And then we can take common factor and we get this product. Right. So we are getting this situation here. This is the product of two factors, which is equal to 2 to the power 2022. Now, obviously, if it is equal to a power of 2, these must be 2 power x and 2 power y somehow, right? And also you have to realize that a and b are positive integers. And if they are positive integers, then a plus 2b minus 1 is greater than a minus 2b, right? So therefore we know that 2 power y must be greater than 2 power x because we are calling this 2 power y and this 2 power x. For positive integers, this is always bigger than this. You can check it yourself. Okay, great. So what we are getting is these two conditions. A minus 2b is 2 power x and a plus 2b minus 1 is 2 power y. If you add them, you get 2a minus 1 is equal to 2 power x plus 2 power y. Now think about it. 2a minus 1 is odd, right? So how can you add two powers of 2 and get an odd number? It's not going to be possible unless one of the powers is 0. Because 2 power 0 will make it 1 and that may help you make it odd, right? So basically what we will say is we'll say x must be 1 because x is the smaller power. We'll put the smaller power as 1. X must be 0 so that 2 power x becomes 1, right? If 2 power x does not become 1, it's the sum of two even numbers, so it cannot be equal to odd, right? So since the left hand side is odd, we are able to say that x is 0, right? And once you put x is 0, you get a minus 2b is equal to 1 and a plus 2b is minus 1 is equal to 2 power 2022 because the product of them must be equal to this. So y must be 2022. And now you can easily solve this. This is a simple equation with variables a and b. And when you solve it, you get the answers. A must be 2 power 2021 plus 1 and b must be 2 power 2020. So again, we are using factorization and then we are using parity. Multiple ideas are being used to eventually get the solution, right? Okay, let's move on. Question 4. Solve in integers the equation xy minus 7 times root over x square plus y square is equal to 1. Okay, this is the problem. Now, let's think about how we do it. Okay, so we can rewrite the problem like this. Xy minus 1 is equal to 7 times root over x square plus y square. And this right hand side is always positive. RHS is greater than equal to 0. Therefore, we know xy is greater than equal to 1 because LHS must also be positive. And now if you do perfect square here, you will get xy minus 1 whole square is equal to 49 times x square plus y square. And we can simplify this a little bit. However, I would like to do a substitution before we simplify it. If we directly try to simplify this right now, I'll end up with terms like x2, xy and all, which I don't want. I want to keep it as simple as possible. So let's do a substitution here. Xy minus 1, let's call it as 70. We know that xy minus 1 is greater than equal to 0. So we know t is greater than equal to 0 also. I'm just doing this substitution. This substitution will help me simplify the problem. Okay. So here this becomes 49t square is equal to 49 x square plus y square. And now I'm getting t square is equal to x square plus y square. Right. So this is the first condition that I'm getting after putting this substitution. Right. Now also let's think about what is x plus y whole square. X plus y whole square is equal to x square plus y square plus 2xy, and x square plus y square is t square according to my result that I got here. And xy, if you see, xy is 70 plus 1. So 2 times xy will be 14t plus 2. So I'm getting x plus y whole square is equal to this thing, which is basically t plus 7 whole square minus 47. because it is t square plus 14t. I'm completing the square here. I need a plus 49. So I put a plus 49 and do minus 47 because I need to make it to equal to plus 2. So I'm getting x plus y whole square is equal to t plus 7 whole square minus 47, right? Why are we doing this? Because this condition itself is not sufficient for us to find both x and y. This is just one condition. We need another condition to solve it, right? So now I got another condition by looking at x plus y whole square, and I will do it on the next screen. So I have x plus y whole square is equal to t plus 7 whole square minus 47. And I also have t square is equal to x square plus y square. And remember what was my substitution? We had xy was equal to 70 plus 1. That was my initial substitution. We have to keep that in mind. So here, if I simplify it a little bit, I can write it like this. T plus 7 whole square minus x plus y whole square is 47. And using the identity, I'll get t plus 7 plus x plus y multiplied by t plus 7 minus x minus y is equal to 47. So it's a product of two integers is equal to 47, but 47 is prime. So obviously this must be 47 and this must be 1, because prime numbers can be only written in a certain way. Product of itself and 1, right? So once I know this, I will easily be able to solve. So I'll say this is equal to 47 and t plus 7 minus x minus y is equal to 1. Adding both of them, I get 2 times t plus 7 is equal to 48. So t plus 7 is equal to 24, and therefore x plus y is equal to 23. And from here I get t is equal to 17 and x plus y is equal to 23, right? And if t is equal to 17, I'm getting xy is equal to 17 into 7, which is 119 plus 1, so 120. So now I have xy product is 120 and the sum is 23. So clearly x and y must be 15 and 8. In any order, it could be 8 comma 15 or 15 comma 8, right? And you can check the original equation. The original equation will even be satisfied with negative 15, negative 8. So the ordered pairs that will solve this equation are these. These are my 4 ordered pairs that solve the equation. The point here is we try to simplify the problem by doing an appropriate substitution. Xy minus 1 equal to 70 does a lot for us. Once you do this substitution, you end up with this equation, and we got this equation by doing x plus y whole square and putting t back into it again, right? After that, it was a little bit of a property of prime numbers to figure out how to solve it, right? Okay, let's move on to the next problem. Let a, b, c, d be positive integers such that a square minus b square times c square minus d square plus b square minus d square times c square minus a square is equal to 2021. You have to find all possible values. Find all possible values of a plus b plus c plus d. Okay. So here there is a temptation to think about something clever, but you can try, but the most obvious solution for this comes only after you expand and simplify this. You have to multiply it out and expand. So sometimes the simplest thing to do turns out to be the most useful one, right? So if you do that, let's see what comes. A square c square minus a square d square minus b square c square plus b square d square plus b square c square minus a square b square minus c square d square plus a square d square is equal to 2021. And a lot of stuff here gets cancelled. A square c square gets cancelled. Actually, a square c square doesn't get cancelled, right? So I will not cancel that. A square d square gets cancelled, I think. This gets cancelled with this. B square, C square gets cancelled here. And we have four terms remaining, you can see. This term, this term, this term, and this term. I will take something common here. Between this and this, I can take A square common. I get C square minus B square. And between these two also, I can take D square common. So minus D square, if you take common, you'll get C square minus B square again. It is equal to 2021. And this is a simple factorization. We get C square minus B square times A square minus D square is equal to 2021. And 2021, you should do prime factorization of 2021 because if it's a product of two numbers, we should know the prime factorization. It turns out it is 43 into 47, right? So once we know that, here we can say that it is the product of factors. We can factorize each term and we'll get C minus P times C plus P times A minus D times A plus D is equal to 43 into 47. So think about it, since everything is a positive integer and here there are two prime numbers, how can you have four factors? The only way you can have four factors is if two of the factors are one. And the only way that will happen is if C minus B and A minus D are both equal to 1, right? And if they are equal to 1, then C plus B and A plus D could be 43 or 47, right? We don't have to actually find all the numbers. We can just find out A plus B plus C plus D because it will be the sum of 43 and 47, which is 90. So the question is done very quickly because the question was asking us for only the sum of the values of A, B, C, D, right? And the problem was solved in a very simple way by simplifying it, cancelling some factors, factorizing it, and noticing that 2021 is a product of 43 and 47, which are both prime numbers, right? So that's about it for this one. Let's move on to the next problem. Question 6. We have to determine all triples ABC of non-zero integers such that 1 minus A times 1 minus B times 1 minus C is equal to 1 plus A times 1 plus B times 1 plus C. It's not possible to solve this equation in one go because you have one equation and three unknowns, ABC, right? So you have to think of something clever. What we will do is we'll take advantage of an identity. We'll just multiply both sides with 1 plus A, 1 plus B, 1 plus C. So we're multiplying both sides of this equation by the same thing. And this side you end up with 1 plus A, 1 plus B, 1 plus C whole square. And this side becomes clearly 1 minus A square, 1 minus B square, 1 minus C square, right? Is equal to 1 plus A, 1 plus B, 1 plus C whole square. Now this question becomes very easy because you have to realize that this side is always greater than equal to 0. However, if the numbers ABC are non-zero integers, then they must be modulus of A, modulus of B, modulus of C must be greater than equal to 1. So even if they are positive or negative, always 1 minus A square, 1 minus B square, 1 minus C square, all three of them will either be 0 or will be negative. It's either 0 or negative for each of these factors. So the product can be 0, but most of the time it will be negative. But a negative thing cannot be equal to a perfect square. So which means that the only option for this equation to be true is if both sides are 0, right? And both sides equal to 0 means you can say this is 0 or you have to say this is 0, right? 1 plus A, 1 plus B, 1 plus C is 0. Which means one or more of them will be minus 1, right? Now, after that, you have to think about what will make both sides 0. So if you put A as minus 1, then automatically both sides are becoming 0, right? Correct. And you can put b as +1 then. B can be +1. Basically, you just have to take different cases in this case. So what I would say is check these different cases. A could be +1, B could be -1, and C could be any integer n. That is a possibility. See, B is -1 makes the right hand side 0. A is +1 makes this side 0. Actually, B is -1 makes this side 0 as well. You don't even have to fix C here. C can be anything. And any alternate version of this will also work. By that I mean A could be -1, B could be +1, and C could be n. That will also work. How am I getting this condition? Because right hand side has to be 0, and looking at the original equation, left hand side also has to be 0. So basically you have two conditions now. 1 plus A, 1 plus B, 1 plus C is 0. And 1 minus A, 1 minus B, 1 minus C is 0. So this will be 0 if any one of them is -1. This will be 0 if any one of them is +1. So since the same term cannot be both, you will have to say A is -1 and let's say B is +1. That is enough. You cannot fix C. C can be anything, right? And any alternate version of this is also fine. So basically you can say A can be +-1, B will be -+1, and C will be n, anything. And then permute it over the variables. So by that I mean it could be A is n and B is +-1 and C is -+1. And the other option where B becomes n, that is also true. So this is a nice question where one small trick multiplying the same common factor on both sides converted the problem to an identity where one side was always positive and the other side was always negative. So the only way the equation could work was if both of them were 0, right? And that solves this problem. Now, question number 7, let's look at that one. Prove that for each integer n greater than equal to 0, for each integer n greater than equal to 0, 16 power n plus 8 power n plus 4 power n plus 1 plus 2 power n plus 1 plus 4 is the product of two integers greater than 4 power n. So basically we have to prove that this thing is a product of two integers greater than 4 power n, or we have to basically factorize it somehow, right? And it also shows that that number will be a composite number, right? So it's all about proper grouping here. So let's think about it. 16 power n plus, let's group 4 power n plus 1 plus 4 together. And we'll put 8 power n plus 2 power n plus 1 together. And here you can see that this is 4 power 2n plus this term is 2 squares. So this should be a middle term. So 2 into 2 into 4 power n. Think about it. This is 4. This is 4 power n. So it becomes 4 power n plus 1. So it is fitting perfectly as a perfect square. And then we can take 2 power n common here. You get 4 power n plus 2, right? And this becomes what? This is 4 power n plus 2 whole square. Plus 2 power n, 4 power n plus 2. And now you take 4 power n plus 2 common. And you end up with 4 power n plus 2 plus 2 power n. And that is the factorization which shows that this big number is a product of two numbers, each of which is bigger than 4 power n, right? So that finishes off this problem. It's a direct factorization question. Okay, let's move on to the next one. Question 8. Okay. In this problem, we have let m and n be positive integers Let m and n be positive integers. Prove that 27 to the power 2m plus n plus 1 plus 27 to the power m plus 2n plus 1 minus 27 to the power m plus n plus 1 plus 1 has a proper factor, greater than 6 into 27 to the power minimum of m and n. That is a problem. It's framed a little strangely because you have to prove that a proper factor exists for this expression, but the factor is bigger than 6 into 27 to the power minimum of m and n. So minimum of m and n means the lower exponent we have to take, either out of m and n, right? Okay. But also the structure of the numbers themselves suggests that it has to do something with cubes, because 27 has been used, 1 is there, these numbers are perfect cubes, right? So we will think along those lines. So let's rewrite this expression as 3 to the power 2m plus n plus 1 whole cube. That is the same thing as 27 to the power 2m plus n plus 1. Then it becomes 3 to the power m plus 2n plus 1 whole cube. Then you also have this 1 here, right? So what can we do about the 1? Let's write the 27 power first. This is 3 to the power 3m plus 3n plus 3 plus 1, right? So, right. So 1 can be written as 1 cube, and I'm going to try to fit the identity a cube plus b cube plus c cube minus 3abc. There is an identity that a cube plus b cube plus c cube minus 3abc is equal to a plus b plus c times the other factor is a square plus b square plus c square minus ab minus bc minus ca. So I'm going to try this identity. Let's think of this as a, this as b, and this as c. So let's check whether this fits 3ABC or not, because if it doesn't fit, then it doesn't work. So 3 times 3 power 2m plus n plus 1 times 3 power m plus 2n plus 1 times 1 is equal to what? This is 3 power 3m plus 3n plus 3. So notice that this term is the minus 3ABC term, right? So that means that this big expression can be factorized in this way. This way means we have a plus b plus c as a factor, right? So we can write that 27 power 3m plus n plus 1 plus 27 power m plus, not 3m, it was not 3m here, it was 2m. m plus 2n plus 1 minus 27 power m plus n plus 1 plus 1 is, we are able to factorize it in the form a plus b plus c. And what was a? It was 3 power 2m plus n plus 1 plus b was 3 power m plus 2n plus 1 and c was 1. So this multiplied by terms like, we'll get the a square plus b square plus c square minus ab minus bc minus ca type situation here, right? So we are able to, I'm not writing it because this is some number and we are able to factorize this for sure. And now notice that this is definitely a factor of the original number, right? So we have to prove that the original number has a proper factor greater than 6 into 27 to the power minimum of mn, right? So let's try with the first factor. If this factor is greater than that, then we are done. So let's think about it. 2m plus n will be greater than the 3 times minimum of m and n. And similarly, m plus 2n will be greater than the 3 times minimum of m and n. Take two cases to prove it. If minimum of m and n is m, then this is saying that 2m plus n is greater than 3m, which is obviously true because n is greater than m, right? And it works in either case, right? So this factor we can say is 3 to the power 2m plus n plus 1 plus 3 to the power m plus 2n plus 1 plus 1 is greater than equal to, this becomes 3 into 3 to the power 3 times minimum of m and n plus 3 into 3 to the power 3 times minimum of m and n plus 1, right? What have I done here? Because the power here is greater than this, 3 to the power 2m plus n will be greater than 3 to the power 3 times minimum m and n, right? I've just used that. So this becomes equal to 6 into 3 to the power 3 minimum of m and n plus 1, which is equal to 6 into 27 to the power minimum of m and n plus 1. So I have proved that this factor is greater than 6 into 27 to the power minimum m and n plus 1. And actually that is what we needed to do in this problem, right? So even if one of the factor is greater, our problem is proved. And here we use the identity a cube plus b cube plus c cube minus 3abc and its relevant factorization. Right. Let's go to the next problem. Prove that for any positive integers m and n, 8m power 6 plus 27m cube n cube plus 27n power 6 is composite. It's a very similar question. We need to show that it is composite. So we need to prove that it has a factorization into two numbers which are greater than 1. If it was a prime number, it can be written as itself times 1. But if it is not a prime number, if it is composite, it can be factorized into two parts where each of the numbers is greater than 1, right? So I'm going to again use the identity a cube plus b cube plus c cube minus 3abc can be written as a plus b plus c times a square plus b square plus c square minus ab minus bc minus ca. And we are going to try to do that here, right? Why? Because I can see clearly this is something cube. This is also cube of something. This term, I'm not so sure right now. So we can say this is 2m square whole cube plus 3n square whole cube. And I don't have a negative term. I need to make a negative term. So I'll just put let's put a minus 27 m cube n cube plus 54 m cube n cube. And let's see whether it works for us or not, right? So this can be written as plus minus 3mn whole cube. And this is 2m square whole cube plus 3n square whole cube. And now I have three cubes, a cube, b cube, c cube. I need to check whether the minus 3abc term fits this or not. If it doesn't fit, then this is not going to work. So let's check this. Minus 3. A is what? 2m square. B is 3n square. And C is minus 3mn. So we are getting 3 into 3 into 3, 27 into 2, 54, which is going to be the positive sign, 54 m cube n cube. So clearly now you can see that this is minus 3 times 2m square times 3n square times minus 3mn. And basically the whole expression, this expression is fitting in the identity aq plus bq plus cq minus 3abc. And if it does so, now we can factorize it easily. We can just write it as a plus b plus c times this expression. If you do that, you will get something like this. 2m square minus 3mn plus 3n square. And inside, after simplifying, you will get these terms. 4m power 4 plus 6m cube n plus 3m square n square plus 9mn cube and plus 9n power 4. And you can show that this term is greater than equal to 1. The reason is it can be written as twice of m minus n whole square plus n square plus mn. And since m and n were positive integers, n square plus mn is positive and this is positive. So this is greater than equal to 1 for sure. And this number here is also greater than equal to 0. It's actually greater than equal to 1 because we have positive integers mn. It is obvious that m and n, all these terms will be positive, right? So we are able to express this thing as the product of two different positive integers which are not 1. So therefore it must not be prime, it is composite instead, and that finishes off our proof. So in this video, I looked at basically 9 problems where we did factorizations primarily. Some of the problems we also used ideas like prime factorization, ideas like parity, and so on. And that should give you a head start into like being aware of factorization as a technique in solving number theory problems. In the next videos, we'll look at different aspects of problem solving in number theory. I'm focusing primarily on number theory right now because I want to finish off my Udemy course, and you will see more frequent videos starting now. I'll be making more content soon, so stay tuned and look at the Udemy courses if you're interested. You will find a lot of courses coming soon, and already there are enough courses for you to prepare for INMO and other exams. So that's it for this video. I'll see you next time.